Okay, so okay, density is mass over volume. It's usually in grams per liter or grams per milliliter. You'll see both here. Just make sure you pay attention to the volume part, whether it's liters or milliliters. Now, this was utilized a whole bunch. Excuse me. This was utilized a whole bunch during the gold mining days. There's a chemical called iron pyrite that looks just like gold. It's shiny, it's yellowish looking, and it's not gold though. So the way the assayers figured out whether you're bringing in gold or iron pyrite is through density. So what they did is they measured the volume and they weighed it and calculated the density. If the density didn't come out to be gold, it was almost worthless. Now gold goes for, gosh, that's really expensive these days. Like $1,600 an ounce or something crazy like that. And the electronics industry uses gold a lot because it's a very high conductor of electricity, plus it doesn't corrode. So it's highly sought after. Fortunately, you can have extremely thin coats of it, but it's still expensive. When you get a ring, gold is very soft, very malleable, meaning it wears. Now, something that costs $1,600 an ounce, you don't want it to wear away. So what they do is they mix it with gold, or excuse me, mix it with copper, and the copper makes it stronger. And that's where they come in the term carat, like 16 carats, 12 carats. That's how much gold is there versus the copper. So for things that need to wear, they want to harden up that gold. The only problem is it changes its value. And also it changes its appearance slightly. Some gold is very yellow, some gold is not. They even have white gold. So a lot of interesting things you can do with mixing in different metals. Okay, so let's do an example problem with density. Now you're going to be doing density in lab today. In fact, now here's an example of a density problem. The lead strip has a mass of 741 grams and a volume of 0.654. Who knows what cubic centimeters? What's another name for a cubic centimeter? Anyone know? It's called a milliliter. So cm cubed and ml are the same thing. So frequently you'll see them interchanged, unfortunately. So this is the same as 0.654 milliliters. What's the density? And then you can tell whether it's pure lead or not. Now you're going to be looking at pennies today. You can be calculating the density of old pennies and new pennies. Old means prior to 1984. New pennies are after that. And there's a change in those pennies. One, we went from pure copper to zinc coated with copper. It still costs more than a penny to make these new pennies also. I think we should do away with all coins personally, but anyway. So you're going to be doing a couple calculations on density today. Now, there's a couple different ways. Volume is always the trickiest part on density. Mass is easy. You just dry, make sure it's super dry, and then you weigh it. Volume is the deal. Now you can calculate volume two ways. If it's a regular solid, like a rectangle, you use simple formulas to do that. But what if it's not? What if I wanted to find the volume of this thing? How would you do it?
Archimedes method.
Exactly, through displacement. Archimedes was the guy that came up with that concept. So when you get in a tub of water, what does the water do? It goes up. Okay, it goes up by the amount of volume your body has displaced. So if you're totally underwater, the amount the water went up is how much volume you have. Now, when you sometimes if you're into health stuff and you want to find out your fat percentage, sometimes they'll do it through immersion. Also, if you're baptized, immersion as well. So we can do it by displacement or using Archimedes. So if we took this, I took a graduated cylinder, fill it with 50 milliliters of water, and I drop this thing in, assuming it doesn't float, and the water goes up to 65 milliliters. What is the volume of this? 15, because the difference, the delta V, the delta volume is 15 milliliters. Doesn't matter what it looks like. It could look like this. It doesn't really matter what it looks like, its shape. And that to me is the most, it's much more accurate than trying to use formulas for this, because it's got little bumps on it and everything. You have to account for all the little bumps, what the taper is here. This would be hard to calculate. So the displacement method is the preferred method most of the time when you're calculating volume. So that's how that was obtained. Okay, so let's see. I need to write down the numbers here. So I have to change screen. So let's do this problem. Okay, 741 grams and 654. Now, a couple things in this problem. Any number less than 1, put a 0 there. With 0.654. The reason for that comes from the health industry. There is a number of hospitals throughout the United States that had some medical problems created because that was before the electronic stuff. They were writing down by hand, and they splashed water on their paper. And the water hit the ink on the paper and created a dot. So instead of being 0.654, ended up being 6.54. And children have died and adults have died in the hospital because of that. So always put a 0 if it's less than 1. Just get in the habit of doing it. Now, when you put it into your calculator, you don't have to put the 0 in, but on paper, you should always have the 0 there to indicate that it's less than 1. So there's no mistaking about it. Okay. All right. So let's do this problem. Okay. So you have 7. Now, if you're given volume and you're given mass, you automatically just divide volume into the gram. Very straightforward. And you're always going to be using the correct number of sig figs, like always. Okay. So our answer has how many sig figs? 3. So we go to the 4th place and we drop it because it's 0 to 4. So the answer is 11.3 grams per milliliter. Now, if you're given density, yeah,
So because centimeters here is equivalent to meters.
yeah, you can swap them out. But when you see ML, knowing that swap out's available, keep in mind that's the same as, and by definition, by the systemic international units, internationally accepted units, 1 milliliter of pure water is 1 centimeter by 1 centimeter by 1 centimeter at standard temperature and pressure. So whenever you have a 39 milliliters of water, 39 grams, because the density is exactly one. Yeah.
So our answer should be in milliliters. We're starting with centimeters.
To be real honest with you, I'll accept either one. So whatever you feel most comfortable doing is fine. But when you're doing problems, though, you'll see both. So you just need to be aware of that. Okay, so if you're given density, like here we've got 19.3. I can't write on this screen, that's why I have to put up here. So 19.3 grams per milliliter, because that's for gold. And 121 cubic centimeters. So what is the mass of that? Okay, so we want to know, we want to calculate grams, and we're given 121 to start with. So our conversion factor is going to be grams over milliliters or centimeters cubed. Cubic centimeters cancel. And it's a simple multiplication. And these two problems come directly from that worksheet I gave you. Now, in the quiz tomorrow, I will choose one of those problems in the worksheet I gave you directly. And so you have the answers. So theoretically, not theoretically, you do have the answers to all the quiz problems tomorrow. Okay, so does this density stuff make sense? Is everyone clicked off the attendance today? Anyone not? Okay. Now I want to talk about the periodic table. This is what the periodic table really looks like. It's much skinnier than the one up there. The problem with this one, it's a pain to use because it's so skinny, very awkward, especially in books, etc. So what they've done is they've pulled out this piece here and then took this whole thing and slid it to the left. And that's what this is. So all these elements here go in there. So for me, this is the last time you're going to see this particular periodic table. I think it's clearer to use than that one. It's just that you'll never see it. So the other problem with this is for that to fit on that periodic table there, the font would have to be much smaller and harder to see. It's another reason they use that one. Okay, so let's talk about periodic table. Periodic tables developed quite a while ago by two people in Europe. One was a Russian and the other one was, I forgot. The Russian's name is Mendeleev. You've probably heard of him. He was a physicist. The other guy was a geologist. The other guy created this idea before Mendeleev did, but Mendeleev published before the other guys. So Mendeleev is known for inventing the periodic table. He really didn't invent it. He just observed some characteristics. So what he observed was all the elements 150-ish, 180 years ago, something like that, they had different properties, they had different chemical properties, different masses, etc. So what he did is he was a very organized guy and he tried to figure out how can I organize these elements in some logical fashion. So what he did is he put them in order, starting with hydrogen, big long train. And then he wrote down all the chemical characteristics for each one of those. Now, they didn't know about a lot of elements in those days. There weren't 118 of them. There were probably 20, but still, the ones he had at that time, he put in order. Now, this is a one-dimensional periodic table, but the one thing he found was that every now and then, the chemical characteristics were the same. As you go along, same. So what he did is he had an idea is to create a two-dimensional periodic table. So every place where the characteristics were the same, he cut that and moved it over. Repeat it again, he cut it again. So that's how we end up with this two-dimensional periodic table. Now, the cool thing about what Mendeleev did was there were a lot of holes in this. But the way he organized the periodic table, you could predict what the unidentified element is based on how he described the chemical characteristics. Okay, so this guy here, the way he organized it, everything in a column has similar chemical characteristics. And we're going to see during the middle of the semester exactly why that is so. We're going to actually look at the distributions of all the electrons in each element and how they are similar. And that's why the chemical characteristics are similar. It's because the electrons in the outermost orbital are the same organization. So all these have similar chemical characteristics. And you're going to be responsible for knowing some of these. You need to know 4 groups here. So let me get a more conventional periodic table by running over to Oops. That's the same one. I don't know. Okay. So this is the modern periodic table. And this, all this stuff here goes right in here. It's nice and long. Now the modern periodic table, we go all the way out to here, which is 118. Now, from 92 onward, those are all synthesized elements. 92 is the last naturally occurring element. That's uranium. Anything past uranium, in terms of size, there's neptunium, plutonium, berkelium, California, all this stuff. And these are named after the people that kind of use their cyclotrons, et cetera, to discover these new elements. When I was in graduate school, SG is named after Seaborg, Seaborg. He was one of the physicists, actually physical chemists, that discovered this particular 106 element. He used to come to our graduate seminars all the time. I went to Davis, and every week we had a seminar we had to attend. And I was in a graduate group, and the graduate group was from chemistry, food science, weed science, environmental toxicology, enology, beer making. All those had graduate students in them, and they would attend our seminar. So it was a very interesting seminar because you had lots of different applications of chemistry, and mostly biochemistry, actually. Anyway, so it was very interesting. And Seaborg found those so interesting. He would drive from Berkeley, not every week, but maybe once every 2 months or so. He would drive there and attend our seminars. It was really kind of cool. He's a very tall guy. He's about 6'6", fairly thin, and he was pretty elderly then too. He's since passed. But he was part of the Manhattan Project. Who's heard of the Manhattan Project? Okay, a number of you have. Manhattan Project, the United States in 1941 put together a program to invent the atomic bomb because Germany was doing it at the same time. Huge project. Then there were 3 main sites, one in Tennessee, one in New Mexico, one in Washington, actually, and Berkeley participated quite a bit in it. And anyway, he was one of the participating scientists in that program. He's a very cool guy. All right, so let's now talk about this. Okay, so okay, so these are called groups. Okay, so the groups represent the columns on the periodic table. Groups are groups have similar chemical properties. So again, lithium, sodium, potassium, etc., all the same thing. Now, let me show you how useful that is. Okay, I went to the doctor yesterday. I really didn't, but just as a story. And the doctor said, I have high blood pressure. Actually, I do, but anyway. And he said, you'd have to get over this salt you're putting on your food. Whoops, better go over here. As you know, that's the chemical formula for sodium hydroxide. Yes. Is that better? Okay, sodium chloride. Now, the thing about sodium chloride is, if you like to cook, and I cook all the time, the chloride is the part of sodium chloride that makes it salty. The sodium is the part that contributes to high blood pressure or hypertension. So, knowing what you know about the periodic table, how would you suggest I fix my problem where I like salty foods, but I can't have sodium? How would you suggest I fix this problem? Yeah.
Potassium or lithium chloride.
Okay, so if I chose a chemical that's in the column of sodium, remember, these have all the characteristics of sodium because they're in the same group. So there's one on either side of sodium. One is lithium, one is potassium. So I'm going to go to the store now. I'm going to go to the spice section of the store, and I'm going to look through all the stuff. There's a whole bunch of salt. There's kosher salt, there's fine salt, there's sea salt. It's all sodium chloride though. And there's one little part where you can buy potassium chloride called light salt, L-I-T-E. And what they've done is they said, well, the K doesn't make it salty, the chloride does. So I'm going to take the potassium and the chloride and use that. So now it's salty still. It's not as salty, but it's definitely salty. And I don't have this issue of the sodium giving me high blood pressure. And it's all because of the periodic table. Another example, calcium. What does calcium do in your body? Bones, right. And what's on the inside of a bone? Bone marrow. What does bone marrow do? Yes, it creates red blood cells. So when we have radioactive fallout, for example, when Chernobyl went crazy, that fallout from that blast from the power plant spread all over Europe and even here. When Japan's power plant melted down, same thing we got on the West Coast, we got all this fallout. And strontium frequently is one of the candidates for becoming radioactive during that explosion. So here we have radioactive dust being spread on fields around our area here. What grazes on the fields? Frequently, you have a pasture. Yeah, it could be horses and cows. And what do we get from cows? Besides meat, you have milk, right? Okay. And what's in milk that everyone says is good for you? Calcium. Builds strong bones, right? The problem with that is, look at what we have here. We have strontium. So your body will take in strontium if it's there along with calcium. The problem with strontium in the case of fallout is it's radioactive. So people that ingest a lot of strontium that's radioactive, they end up with leukemia because it goes to the bones, it prevents the bones from creating red blood cells, hence leukemia. And it's all because of strontium is in the same group as calcium. Carbon, silicone. You ever wonder why you use silicone a lot for body parts? Because of the same family as carbon. Same chemical characteristics. So this whole idea of groups is very, very important. Okay, so you're gonna need to know 4 groups. And there's a name for every group. Some of them are just named and you never hear about them again, but these are used a lot. Okay, so the first one is alkali metals. Second one is called alkali earth metals. And they have similar names just because their chemistry is fairly similar. The second to last one is called halogens. These last 2 are probably the most commonly referenced. Halogens, and the other one is called now, depending on what textbook you're reading or paper, whatever, they're either be called noble gases or inert gases. The problem with calling it inert gas is we found out they aren't as inert as we originally thought. So noble gases is probably used more than inert gas, but it depends on what you're reading. It'll refer to either one. Now, the reason why they call them this, noble gas and inert gas, is because everything in the periodic table by itself is very reactive, very unstable. But these guys here, they are very happy by themselves. Krypton, neon, argon, helium. That's where it gets its original name, inert gas. Inert means it's not reactive or it's very stable. So anyway, they started going by noble gases. And the reason why they named it noble goes back to Europe. The nobility did not associate with the common folk, the plebes, the plebeians. They only associated with themselves. So they were kind of special group of people, unfortunately. Okay, so that's kind of where they got the idea in these. Since these don't associate with anything over here, they're kind of like the nobility it was in Europe. Okay, so those are the 4 groups you need to know. Alkali metals, alkali earth metals, halogens, and noble gases. Okay, all right, so let's talk more about how this is all organized. Okay, when we go horizontally, those are called periods. Now, periods don't have anything chemically similar. There's some trends I'm going to talk about in a minute. Basically, when you go across here, the atom size gets smaller. And also the electronegativity, which I'm going to talk about again, gets greater. But there's no chemical similarity like there is in a group. Periods go by period 1, 2, 3, 4, up to 7, or you'll see them as shells. Just like a clam shell. Shells 1 through 7. So we have periods and groups. Now, if we took the individual elements by themselves, there are 3 kinds. Noble gases, that's one kind. You also have metals. And what's the opposite of a metal? a non-metal. So we have metals and non-metals and something in between. So let me show you what that looks like. So we have metals on one side of the yellow, non-metals on the other side. And in between, we have combination of a metal and a non-metal, which is called a metalloid. So the metalloids are very interesting elements. And on either side of the squiggly black line are where they lie. Now, depending on what book you're looking at, they list them differently. But basically what I want you to know is that this line is a demarcation between metals and non-metals. Now, the thing about metalloids, I even have a hat that says metalloids are cool. My students got for it. And what's cool about metalloids is depending on what voltage you apply, it will act differently. So this is what I mean by that. In 1947, AT&T, which is known as Bell Labs at the time, let's use germanium as an example, and found that if they apply a current to that metalloid there, this will either conduct or not conduct. Now let's look at the properties of metals and non-metals. What's one property of a metal? Yeah. Conductive. Electrically conductive. So guess what on non-metals? Is it conductive? No, it's the opposite. So not. What's another characteristic of a metal? Yeah. It's reflective or shiny. What else? Yeah. Yes, so is a non-metal. So keep that thought though. Yeah. Malleable. Good, good. So malleable means you can bend it, shape it. You can pull it or compress it. Pull and compress. Okay, and a non-metal is going to be brittle. So I used to do a lab up in Washington, and one of the labs was we had all these metals and non-metals out. And the students had to determine which was a non-metal and which was a metal. So the first thing they did, we had an anvil there. They took the element and went like this with a hammer. Bam! If it shattered, guess what? Which non-metal. And if it just went, bleh, it was a metal, malleable. Shape it. And it was a kind of a cool lab because it got really loud. people banging on this anvil. Okay, so a metalloid will change so we can convert metalloids from acting like a metal to acting like a non-metal. It'll either conduct or not conduct. Now, going back to 1947 with the Bell Labs, they found that they took a germanium, which is a metalloid, applied a positive current to it, it was conductive. They applied a negative charge to it, it was non-conductive. And so they started messing around. Now that's a wire coming off the top, and it's just a little crystal of germanium. So what they found is if they could turn this on and off electrically by applying a charge of negative or positive. So what they invented, who knows what they invented in 1947? Anyone? Yeah,
Transistor?
transistor, yes. Think about, I didn't bring my watch today. Think about all the stuff that we depend upon today's society, you know, electronics. And what they've done is they've taken these transistors, which were originally big. I mean, we're talking about that big around, about that high. They were big. Now you're talking about a printed circuit board with probably millions and millions and millions of resistors and transistors all on a little bitty card. But in those days, they invented something called the diode. Diode is the simplest form of a transistor. Di meaning two, ode meaning terminals. And depending on what the voltage was going into these, it either conducted or not. Now these are used a lot, turning alternating current into direct current. Because alternating current goes positive, negative, positive, negative. So when the alternating current went in here, on the positive side, it conducted. When it went negative, it stopped producing. So basically you ended up creating direct current from alternating current using a metalloid and the diode. So metalloids are really, really revolutionized our world. Big time. Okay, so you need to be able to identify three kinds of elements: metalloids, non-metals, and metals. Yeah.
Are the metalloids like first ones on the other side?
Yeah, the main thing is once you draw a blob there,
Like,
because it depends on what book you're reading. Sometimes they, yeah, so just go kind of the way I did on the yellow up here. You know, you could go like that. Main thing is to know the concept of a metalloid. It's really kind of cool. Okay. Let's see, let me do one thing here. Okay. We are going to talk about some trends observed on the periodic table. The one that's frequently used called electronegativity. Now, we're going to abbreviate that EN, uppercase, because electronegativity, pain to write all the time. All the elements exhibit a different electronegativity based where their location is in the periodic table. Now, when we get into some further analysis later in the semester, we're going to know why that trend exists. But basically, fluorine, top right, goes down to bottom left, francium. So what is electronegativity? Who's heard of electronegativity from your past days? Okay. The easiest way to think about electronegativity is the tendency. Let me type this down. Better type this down. Okay, so electronegativity is a tendency for one atom to attract an adjacent atom's electrons. Higher electronegativity, the more that tendency is. It wants to pull that other atom's electrons away. Fluorine being the strongest, francium being the weakest. So that's trend number one. Trend number two is size. Size goes in the same direction. Fluorine is the smallest. Francium is the biggest. Now, there's two reasons for that. One has to do with electronegativity. And two, francium has more stuff in it than fluorine. So if you have a bag of 10 marbles versus a bag of 66 marbles, the 66 bag is going to be bigger because there's more stuff in it. So that's one reason this trend exists. The other one is electronegativity. The higher the electronegativity is, the more compact the atom is. Now, the size is measured from the outermost electrons. Because all the elements except for hydrogen have multiple electrons, and they're organized in a way. Some are closer to the nucleus, some are further out apart. So when you measure size, you're talking about the outermost electrons. Okay, let's see. Trends. I want to talk about atom organization. And then we're going to get back to the periodic table. Okay, the atoms at the most basic level are made up of three kinds of particles. Okay, neutrons and protons are in the nucleus of the atom. And electrons, where are they located? This is a trick question, yeah.
Around the orbitals.
That's right. What else? Where else?
Oh, they're also a component of the neutrons.
Yeah, exactly. So they're inside of the nucleus as well as outside the nucleus, and they're buried inside of a neutron. So a neutron's made up of an electron and a proton together are a neutron. So that's how you can get an electron inside the nucleus. And when a neutron breaks up, it produces a proton and an electron. Or if they combine together, you'll produce a neutron. So electrons are available in the nucleus. And remember, that's buried inside of a neutron. And outside in an orbital. Okay, and each of those three particles have a charge. A charge. The protons here, oops, I have that mixed up. Okay, so a neutron has a charge of 0 or no charge. Proton has a charge of +1, electrons -1. The +1 and the -1 are exactly the same amount of charge, just opposite. And they measure that in coulombs. Okay, so atoms exist in two forms. One form is a neutral atom. A neutral atom means that there's no charge. That means the number of charged particles positive equals the number of charged particles negative. Equal, so they net 0. Hence the term neutral. Okay, so whenever you hear the word neutral, and if it's associated with a charge, it means it's no charge, 0. If charged particles exist, they have to exist in equal numbers, so they cancel each other. Okay, so what if it's not neutral? Then we have something called an ion. So now we have the number of protons does not equal the number of electrons. Hence, there's an imbalance of charge either on the positive side or the negative side. So we have two kinds of ions. If we have more positive protons than negative electrons, we end up with a positive ion. That is called a cation. Now, the word cation comes from in electrochemistry, something called a cathode. So these guys are attracted to the cathode. That's where the cation comes from. Now, this can be +1. +1 means it has 1 extra proton. +2 means it has 2 extra. +3, +4, you know, it can get up to like 5 and 6. Not much more than that, though. And then the opposite situation is we have more electrons, hence it's negative. And that is called an anion. And that word is derived from the anode. So these these ions are attracted to the anode. So this is based on cathode, anode. And the important part of knowing that is cathode, if you think of the T as a plus sign, and that's associated with a positive ion. If you think of the N there as negative, associated with a negative ion. I don't know if that helps, but. Okay, so if we look at carbon, we look at carbon on the periodic table, there are some numbers. The integer tells us how many protons carbon has. It's also called the atomic number. Okay, atomic number. And we're going to see later, those 6 electrons are not distributed uniformly. They're kind of split into 2 groups. But right now, periodic table says how many protons are there. Now that is a unique number. There's no other element up there that has 6 protons, because carbon has 6 protons. If it's 7 protons, it's not carbon. It would be nitrogen. Okay, so the number of carbons determines that. Now in nuclear chemistry, we change protons all the time. So in nuclear chemistry, we transmutate one element to the other. That's what the alchemists tried to do back in the 1500s. They wanted to turn lead into gold. They wanted to transmutate lead into gold. And we can do that nowadays. It just costs more money than the gold is worth. But transmutation happens all the time. Happens in the atmosphere naturally. When an atomic bomb goes off, it happens big time because the number of protons in those new atoms are different. Okay, so carbon's got 6 protons. And if we're talking about neutral carbon, how many electrons does it have? Based on the definition up above. So you have 6 protons, how many electrons? 6, because it has to balance, because it's neutral. What if we had a cation? We had a carbocation, a cation that's made up of carbon. How many protons will we have? How many protons? 6, because it's carbon. 6 protons. How many electrons? 5 electrons. Because we have to have 1 more proton than electrons to get a charge of +1. That makes sense? What if we had a carbocation +2? How many electrons? 4. So my message here is the electrons can come and go, but the protons cannot. Because the protons change, it's no longer carbon. So electrons come and go, period. Unless we're talking nuclear chemistry, then protons come and go there as well. Okay, a carboanion. How many protons? 6 all the time, no exceptions. It's got to be 6 or it's not carbon. And how many electrons? 7, right. You have to have one more negative particle than positive particle for it to be an anion. Okay, does this make sense? All right. The decimal number is the molar mass. I mentioned this yesterday. The molar mass is the average it's the average of all the naturally occurring isotopes of carbon. They add up to 12.01. The average. You know, when you take an average, you end up always with the decimal number. That's where that decimal comes in there. So next question is what's an isotope? Now, the way you're going to get used to writing elements, you've got to specify a couple things on the elements. Okay, carbon, this is the number of protons down here. So for this to be C, this has to be 6. No exceptions. This number up here, though, has the protons plus the neutrons. So what is different about carbon 12 versus carbon 13? Yeah.
What unit?
Sorry.
What units? Like, for the natural mass?
Good question. There are 2 units. That's a really good question. Thank you. There's 2 units we're going to be using here. Grams per mole and AMU. So if we took a mole of carbon atoms, 602 times 10 to the 23rd, it would weigh 12.01. Or it has 12.01 atomic mass units. Those are used interchangeably. So if you have 1 atom of carbon, we talk about atomic mass units. If we have a mole of them, we talk about the molar mass. 602 times 10 to the 23rd. So that's the units of this. Okay, so let's look at let's get back to this here now. How does carbon 12, so the other way to write this would be carbon 12, carbon 13. So the carbon refers to the symbol, 12 refers to this upper number here. Okay, so what is the difference between carbon 12 and carbon 13?
A neutron.
One has an extra neutron. So the chemistry of carbon is not determined by the neutrons, it's determined by the electrons. So frequently when you have a reaction, you have a mixture of isotopes in there, chemically acting like carbon. The difference between them is number of neutrons. Because the protons have to be 6, period, no exceptions. That means it has 6 protons, that means 7 neutrons. 6 protons, 6 neutrons. Which weighs more, carbon-12 or 13? 13, it weighs more by 1 neutron more. So when we look at 1201, what's the more common isotope, 12 or 13? 12 is, because the average is closer to 12, not to 13. Now later on, I'm going to be talking about a weighted average. A weighted average determines by percentage how many 13s we have versus 12s. You can also have carbon-14, used a lot medically, carbon-15, carbon-11, it just depends on how many neutrons are in there. It's a big mashup. Okay. So let's go back to periodic table here. I'm going to end on this. Elements have a tendency to form an ion for stability reasons. Now, in this class, I'm going to stress, if things are unstable, there's a likelihood that they want to become more stable. If they're already stable, what's the point of reacting? Because you're already stable. So the noble gases are very, very stable. I mean, they are happy to be by themselves. Everything here is inherently unstable. So what do you think nature does with things that are unstable?
Stability.
Yeah, wants to become more stable. It does that usually by forming a chemical reaction. So in nature, rarely do you see these guys by themselves. Rarely. That's why gold, silver, these guys are rare, because to form a metal, it's not as stable as the mixture or the compound. And usually it forms, because we have oxygen so much in the atmosphere, usually it forms an oxide. So most minerals, when you take it out of the ground, is an oxide. So you have to convert from the oxide to the metal. For example, uranium. Common form of uranium is uranium oxide. It's around the country a lot. In fact, if you go to Arizona in the Southwest, you can buy pottery on the side of the road. Uranium oxide is yellow. So they mix that in with their glaze and color their pottery. The bad part is some kinds of uranium are unstable. Others are very stable. In fact, up in my Tacoma where I taught, we had a whole set of radioactive pottery. Because we bought it, I didn't buy it there. Someone bought it on the side of the road in Arizona. Okay. Okay, the alkali metals like to form a +1 cation. All of them. And as the semester goes on, you'll see we start breaking down how the electrons are organized in these elements. You'll see why they like to form a +1 cation. The alkali earth metals like to form +2. And we're going to jump over to, and by the way, these groups frequently go by numbers. So this is group 1, group 2, 3, 4, 5, 6, 7, and 8. The ones in the middle don't behave as nicely as the ones on the outside. Okay, so we're going to jump over here to group 3. They like to form a +3 cation. What would you predict for the next one over? +4. Well, let's jump over to the noble gases. What kind of an ion do you think they form? Because they're neutral and they're inert, that means they don't form an ion. Okay, going from right to left, the halogens like to form a -1. The next group over, a -2. -3. And what about the next group over from there? -4. So the problem with group carbon, it doesn't know whether to go +4 or -4, so it doesn't form any ion. So you automatically know what ions are formed based on the group. So group 7, they all form a -1. So fluoride, fluorine is the element, fluoride, IDE is the anion -1. So there's fluoride, chloride, bromide, iodide, etc. These guys, -2, -3, no ion, +3, +2, +1.
Does that mean that group 4 is like the more stable?
Yes and no. We're going to see when we talk about bonds. There's two kinds of bonds. There's an ionic bond. And there's a covalent bond. Co means share. Like when you have a cohabitat, you share your apartment with someone else, right? Co. What happens in a covalent bond is the two atoms share electrons. In an ionic bond, you have to have a cation and an anion, where electron goes from the cation over to the anion. And that's where the strength of the bond or the stability comes from. So the idea is we're going to form either an ionic compound or a covalent compound for stability reasons. So those are the two main, we're going to talk about bonding it. But that's in a nutshell. Can I answer your question?
Yeah.
Mostly. I always worry about that. Sometimes I. Okay. All right. So that's what I want to talk about on the periodic table and a little bit on atom organization. So again, tomorrow you're going to have a quiz, and the quiz is going to come directly out of the worksheet I gave you. I'm going to use the exact same problems. And that's all we're going to do tomorrow in lab. It'll be a dry lab. Okay, so Dr. Yee's lab theoretically doesn't get out to 3:05. So I'm going to have to dismantle all this junk here for me to walk over there. So anyway, are there any questions about how things are going in here? Everything's located on, now we almost have enough people for 1X to be a valid class. I have theoretically 9 people. So if you're interested in signing up for that class, let me know. I'll give you an ad authorization number. Okay, I have all the paperwork with me, so I can give you that number today. All right. Okay, so make sure you have all your protective gear on in lab. Make sure you take your backpacks and put them in the back. And you can poke your head in the door. If the lab is done, you can go in. Otherwise, wait till the lab is over.